So, hello. So this is the analysis of a project on social network analysis, and a team name is Pirates, and the team members are Jatin Shrivastava, Viral Garg, and Jitesh Gupta. So we'll start by telling the about databases which we have chosen for a project. So first database is the Amazon MDS database. So we'll tell you about this. So this is an undirected and unweighted graph, and the size of this graph is 3,34,863 nodes, and the maximum degree is 549 edges. So here we are reading the edge list of our Amazon database, and the database is a file is in the form of a text file. So we are using this inbuilt function read underscore edge list to create the database using the network library, and we have named it as nx. So nx.graph and then node type as an integer. Then we have created an object of this srw, rwf, isrw. This is nothing but a class which we are using for random sampling of a database, because we know that a database contains a graph contains a lot many nodes, so we need to sample it. So what we are doing here is that we are doing a random walk sampling on this graph. So here we have made a class which is the same name as I have mentioned there, for which we have created the object. So here we are doing a random walk sampling of the graph. We have given the parameters of the graph and the nodes we have to sample. So then we are applying this algorithm to convert it to do the random walk sampling by skipping some nodes randomly through the graph, and then the output of this is that we are giving the number of nodes which we want in a sample graph. So here we are giving 2000, so we'll get a sample graph which contains 2000 nodes. So what then we are printing the information of our graph. So there we go. There we see that the number of nodes is 2000, the number of edges is 2534, and the average degree is 2.5. Then coming to the centrality measures, then we are taking out degree centrality by using the inbuilt functions. Here in every case we have used the inbuilt functions to take out the centrality measures. So here it is in degree centrality, and we have taken out the maximum degrees, the maximum node corresponding to the maximum degree centrality, the node corresponding to maximum degree centrality. So for that we are using the key of that in the list. So here we are printing it, and then we are drawing the graph for that. Similarly, we have done for eigenvector centrality. We have taken out the maximum value, and then we have taken out the node at which we get the maximum value, and then we have printed the same, and then drawn the heat graph for that. Then we have taken out the maximum eigenvalue and the alpha corresponding alpha value for that, which has come out to be 7.74, and the alpha for that is 0.065. Then we have cat centrality. So the inbuilt function for it is nx dot cat underscore centrality. Then we are given a sample graph and the alpha value. Then we have printed it and then drawn again same graph, each graph for that. Then we have the page rank, the maximum page rank, by using nx dot page rank and then sending a sample graph as a parameter. Then we have taken out the node at which we get the maximum page rank. Then we have printed it. Then we have the closest centrality, the maximum closest centrality at the particular node. Again, using the maximum function to find the key, that is the index at which the index value at which we are getting the maximum value of the closest centrality. Then we have the betweenness centrality. For that, we have taken out the maximum betweenness centrality using the function max and again the betweenness centrality. Then here we get, again we have got the graph telling about the various nodes which have the betweenness centrality. The maximum one being the yellow one. Then we have the local clustering coefficient, and for that we have the inbuilt function nx.clustering, and here is the sample graph which is sent as a parameter. Then we have taken out the global clustering coefficient, and similarly the transitivity of the graph. Then we are printing the corresponding values. Similarly, we have taken out the reciprocity. And now coming to the airport's database graph. So here I'll tell you about this. It is a directed graph which is also weighted, and again the size here is low. It is 1574 vertices, so the nodes are 1574, and the maximum degree here is 596 edges. So it is quite smaller in size than the Amazon MDS graph. So here, since it's a directed graph, so here we are using this as we have created this graph using nx.diagraph, because for directed graph we need to use this diagraph. So then we have G as the sample graph. We have taken this variable in a smaller variable G, sample graph. Then what we have done is that printed the information on this. So the sample graph here, which we have sampled using the algorithm mentioned above, that the number of nodes is 500, number of edges is 5960, and the average degree, in degree and the out degrees are 1192 and 1192. So now here for this we have this degree centrality as an nx.degree centrality, and again the parameter is sample graph. Then we have to find the node at which we get the maximum degree centrality. So for that we have used this key max equal max of degree centrality dot keys till the key we have found is in the degree centrality. So the maximum degree centrality is printed here, and then which is at node, and the key max, that is the maximum key at which we get the maximum. The key at which we get the maximum centrality. Then we have printed the heat graph for the same. Then similarly we have the eigenvector centrality, and we have taken out the same inbuilt functions. Here we are using this value of a constant which is used for taking to get the value of eigenvector centrality precisely. So this value is around 10 lakh. So it is used for getting a precise value of the eigenvector centrality. So here we get the maximum eigenvector centrality, and then which is present at the node. The similar way as we mentioned in the previous degree centrality. Then we have printed the graph of the same. Then again we have the maximum eigenvalue and the alpha part. Then we have the CAD centrality, which is present at the maximum at a node, and then we have drawn the graph of the same. Then similarly we have page rank, the maximum page rank and at which node it is present, and then the graph of the same. So here we see that the page rank is 0.0405 at node 1. For the first node, itself we have this maximum. Then there is the closest centrality. For that we are getting 0.53 and it is present at node number 7. Then we have between the centrality. Here we pass two parameters, the graph and the value of k, for which we need to give a larger value for to get a more accurate value for the betweenness centrality. So it is around 10, which we have chosen for the example. So then we get the maximum betweenness centrality, and which is present at a particular node. Then we have the local clustering coefficient and the global clustering coefficient, and then the graph transitivity, and then the reciprocity. As it is a directed graph, so we know that there is a graph reciprocity will be there. So here's the first part of a project.
Hello, my name is Hitesh Gupta and I am here to discuss the second part of our project. So the second part was to find Ng by N ratio where Ng represents the maximum size of the connected component and N is the total number of nodes. So what we are going to do is I represents our average degree and we are going to increase our average degree by 0.1 for every iteration. So we are going to find we are going to find the maximum connected component size for every iteration. So this is the our probability which is defined by I by 499. So we have generated a random graph by the function and we have passed the number of nodes and the probability. So the graph is generated and we have find the maximum connected component graph in our random graph. So the giant component is this, the giant component size is taken out in the giant component and we can find the ratio of this component by total n. So this is Ng by n and what we are going to do now is to plot Ng by n by our average degree. So we can clearly see that when the graph hits average degree above when our average degree is just greater than 1, our graph likely is increase. Ng by N ratio is increasing drastically. So we can here see that it is a subcritical part and this is the supercritical part. So thank you. Hello, my name is Jitesh Gupta and we are going to discuss about the information cascading effect in the network. So we have taken a simple social network dataset called Live Mocha and the network is undirected and unweighted. So what we are going to do is first download the Live Mocha CSV from the Cornet website which is freely available. Now we have made a networks graphs by using networks library in the Python. So now for each row we add an edge between the two nodes. So the graph is created by using this data set. Since the graph is very large, so we used random walk sampling for our sample graph. So G now hold the sample graph and the information about the sample graph is number of nodes is 2000 and the number of edges around this much and the average is average degree of each node is 2.15. So to initialize the initial number of activated nodes, we use a simple random number generator. So we used to generate a random number between 1 and 500. So the here we got 139 nodes. So initially 139 nodes will be activated by our algorithm. So now for the activated set, to find which nodes are activated by our algorithm. So we take random node between 1 to 2000 because these are the only nodes which are in our sample graph. So we add them to our activated list. So these are the all 139 nodes which were initially activated. So let's go for this remaining activated. Remaining activated is nothing but our activated list, which is initialized by our activated list. So while length of remaining activated for each, so what we gonna do is for each node in the remaining activated, we are gonna remove that first and find its neighbor by g dot neighbors, and for a particular node we are gonna look for our neighbors. So if for child in neighbors, if child not in activated, if the child is not already activated, we can do probabilities, some maths. We are going to define a probability. We are here going to define a probability. If a random number generated by this random dot uniform is less than 0.4, we are going to activate this child. Okay, and we are going to append this child in the remaining activated. If the child was already activated, we are not going to activate it one more time, because it is in the algorithm we can only do it only once. If it is already activated, it has only one chance to activate its neighbors. So if child is not activated, we are, or if we can activate it, if the probability is less than 0.4, yes, we can definitely activate it and append it on the remaining activated. So for the next step, when this node shows up in the while loop, we can go through its child and check if it's already activated, so we don't activate it furthermore. And if it is not activated, we can do some probability maths. If the probability comes up to be 0.3, or so we're going to activate it, or it's come to 0.6, so we will not activate it. So after the run of this algorithm, we have some we were having initially the random activated nodes were 139 and the final activated nodes were 364. So we can here see the large number of nodes are activated by this algorithm. So this is so this shows information cascading models. So let's analyze this graph. This graph is made by those who were activated were colored red, and those who were not activated but were colored black. So by the nx.draw, we have drawn the graph. So these red lines, you can see that red, and these are the neighbors who were activated during the information cascading effect, and the black ones were not affected because their probability turns out to be low. So thank you.